If we look at hotspots worldwide, there are some clear examples, like Galapagos is an easy one. Over here, where the hotspot currently sits, there's a trail that leads back to, it turns out, most of the Caribbean plate is the big burst out of the Galapagos. Right? Iceland is kind of all sitting in one place. It's harder to tell what's going on there. But places like Samoa and Easter Island over here, Tristan da Cunha, Afar, Réunion, that goes to the Deccan Traps in India, a famous one. Kerguelen's kind of got a big blob over here. That's kind of a little bit more complicated. I'll have to go into that in a little more detail. But it turns out that quite a lot of these hotspots do have large igneous provinces attached to them. Sometimes easier than others, right? Here's Yellowstone over here. Over here, kind of worn out for our North American viewers. And so all over the place, right? So Hawaii is over here. It has a trail, and it's cut off. So we don't get to see, actually, on the surface today, very easily attached to where it used to be, what started off Hawaii. But it's a natural question, so we will explore that. And the way to do that is kind of look at the reconstruction of the plates, and I'll get to how this is done here shortly. But it turns out that 140 million years ago, the Pacific Plate was born out of the middle of three other plates. One called the Izanagi, one called the Farallon, and one called the Phoenix. And out of the middle of those three plates came a little triangle of the Pacific Ocean that grew. And we know this from the magnetic anomalies, which I'll cover also shortly, that have this triangular shape. So we'll point out this triangular shape later on. And it kind of grows. We can kind of track the different magnetism of the seafloor over time and kind of see how the Pacific Plate grows and moves in this direction and consumes the whole Izanagi Plate to the northwest. The Kula Plate still remains at the Farallon over here. Kula to the north, the Farallon over here, and the Phoenix is completely gone here to the south. So the question is then, where was the Hawaiian hotspot during all of this? Because that's what's going to matter. Is like, depending on, this is a canvas, the background of what's happening, and Hawaiian hotspot might pop up somewhere. And then which plate is it on? This plate? Is it on this plate? Is it on this plate? Which way would it go? Is it on the edge? So that's what we'd like to examine next. But to do that, we have to go back to another kind of novel approach of studying the Earth. And that's looking at the magnetic field generated by the core, so it kind of relates to what we're talking about here. But kind of briefly, we have our magnetic field, right? The Earth is like a big magnet with field lines that kind of go from south to north, right? Just like if you put down a bar magnet and compasses next to it, you can kind of see that metal shavings will align in the shape of that magnetic field, very similar to the Earth. So that's just how it naturally is. There's a difference between a magnetic pole and a geographic North Pole. And that may be a story for a different day, not to get lost there as well, right? But so one thing you can measure on this, besides the intensity, is you can also measure on the compass what's called declination. So on my compass view over here on the left, this is the direction, like on the surface of the Earth, right? Which way is it relative to magnetic north? But also there's something called an inclination, which is how much does it dip down from horizontal? What angle is that? Because you might notice that at the poles, that angle is near vertical. And by the equator, that angle is near horizontal. So it turns out that if you can have metal around, and I've mentioned that our lavas are already very iron rich, and you can actually cool that iron in a certain magnetic field and preserve it over time, you can then tell a lot about the history of the magnetism of an area, or a big area, possibly the whole Earth. So this is kind of the basis for that, how the magnetic field works. And the magnetic field is, of course, what provides us the magnetosphere, this kind of protection from these ions that come flying over from the sun at us. And so it's a very important thing to study, how the magnetism of the Earth actually changes, and it's related to all this process of Hawaiian hotspots as well, because that's part of the reason for understanding this core mantle dynamic and what's changing inside of the core. So kind of see in here the spinning core is thought to be spinning in the order of meters per second to generate the dynamo that we see, the magnetism on the surface. So in actual practical terms, they believe that because it's all, the whole Earth is revolving, there's a spin that kind of goes around. Oh, I need a different color. So there's a spin that kind of goes around this way, and then within that you have these other coiling spins that kind of surround the inner core, and it's through those that we essentially are creating field lines, right? This is all liquid flowing hot iron under pressure, and it's flowing at these meter per second rates, and that's what's generating a magnetic field that's permeating the entire planet. All right. So it turns out that from eruptions in places like Oahu and other young volcanics, you can actually go on the cliffs of what are lava flows, and lava flows have lots of little iron crystals, and a lot of them are like little compasses. You can then go and then first of all, you're saying which way is north? Is north towards our current north? And they've drawn that on here as a black bar. And if north, according to the rock, is towards our current south pole, then they've drawn that as a white. And they call these normal and reverse periods. And so here is the whole geomagnetic time scale of the Earth. And this is actually used because you can, it's almost like a fingerprint. If you find a little section that got exactly that pattern, you know it's got to be right there, and it can't possibly be anywhere else on a scale because of that unique pattern kind of fingerprint over time. Right? So 0 is over here, 5 million years, 10 million years ago, 50 million years ago, 20 million years ago, 25, this is 40, this is 80, 120, 165 million years ago. That's how far back we have this magnetic time scale. Beyond that, it gets a little troublesome. We'll get to that shortly. There's not a whole lot of rock left that's easy to make a continuous scale from that point forward. Whereas if you have a hotspot erupting for at least 80 million years, then you have a pretty good record of especially this younger stuff right in there, right? And so some of the cliffs of Oahu and Kauai, you can actually go and you can say, well, part of the cliff is normal, and this part is a reverse, and this part is normal, and this part is reverse. Right, and that's kind of how we come by doing this, and actually then relating it to an actual time. So what you can see is it's flipped a lot. There are times where it's flipped a lot in a short time, and other times where, especially through here, the long Cretaceous quiet zone, it stayed steady for a long, long time. So that can happen too. But we're in a period now where it's been more flippy, with some longer periods, kind of similar to what we see in the last 20 million years or so. The details of that perhaps for another time. But what actually happens then is that as lava comes out of the ocean ridges to form the seafloors, the actual poles of the Earth will flip, and then the iron will point north on one line, and then north in the other direction on the next line. And so we actually have this map of stripes of the seafloor. It's essentially a map of polarity of rocks on the seafloor that ends up being something like this. So that was a fantastic discovery for the proponents of plate tectonics, because that would really allow them to show a lot of this effect in incremental fashion rather than abstract fashion. And it's very useful now beyond that, because we have now this whole map of the Earth, ages of the ocean floor for magnetic anomalies. And what you might find is that the darkest color on here is this dark blue, and that is about 180 million years ago. And it turns out the oldest ocean floor is that age. And that's because universally, when it comes time for an ocean plate to collide against either another ocean plate or a continental plate, then the thing that goes under is always the older ocean plate. So you end up recycling the ocean crust, but you don't recycle the continental crust. That's like the scum on the Earth. Instead, the continents kind of float around. They never really sink in. Whereas sometimes edges of islands will get scraped on continents, and so continents can have things stuck onto them, but they kind of move around on their own, bobbing on the surface as well. And really, what's the more active part of the Earth, the surface of the Earth is all underwater, right? And Hawaii being a little exception right over here, but you can kind of see that the reds are the youngest stuff here, and that's where the active seafloor is spreading. The youngest, this is that giant underwater mountain range. That's the spreading ridge of the Earth. It kind of goes all the way around, loops around, and there's one that goes all the way around Antarctica as well. You kind of follow it all the way around. So a very interesting thing there. And so here is our Hawaiian Hotspot Emperor Archipelago trail on that feature right there. So, and that's where we get the boundaries from the plates. So when we come to tectonic plates, this kind of all comes from the same place. It's the boundaries that we see. There is that same spreading zone right in there, and you kind of see areas where continents are separated from oceans, but that's where the boundaries for continental plates come from, is from that kind of mapping, most of it being underwater, and other parts, of course, being on land, but overall, most of it's underwater. So here's an animation from scotese.com, and this is a reconstruction, right? So if you actually you can rewind by, let's take away the very minimalist layer, and let's put it back, and let's put it back, and let's put it back, and that's how we actually have reconstructed Pangaea. This is an animation from Chris Scotese. I'll play it one more time. This is kind of undoing it, rewinding. He's showing the Atlantic Ocean essentially closing, and now it's going to normally open. This is how it actually went, by undoing all those magnetic stripes. And it's going to see here we are. Hawaii's here, so we're kind of coming around, spinning from the left, the back end of this thing. Right, so not as clear to the center part of this animation, but kind of shows you how this game is played and how we can reconstruct where different plates were at different points in time is from this kind of process, right? So here is Pangaea without the plate boundaries, showing just the continents, and it's exactly that same pattern. So I'll pull it back and forward again. Same thing. Another Chris Scotese animation, who's fantastic. He's been doing this ever since the time when he had to do it on paper and do flip books for us to see animations before there was a YouTube. All right, so that was Pangaea. And one more kind of showing in a map view how we got from Pangaea to the whole Earth by kind of opening up sequentially all the ocean plates. So that's it. That's how it works. And so if we look a little more closely at Hawaii, what I've done now is I've taken this color scheme and I've superimposed it for the same ages on the Hawaiian Emperor chain. So you can kind of see that even though we are on this kind of greenish material over here, which is in the 50 million year range, 60 million year range, we're actually burning through it most of the way, right? A little bit slower over here at this far north end. But we see a stark contrast in color for what's actually coming out to what's actually there. And the bend relates around 47 million years ago. And we're still going to come to that, I promise. And if we look in more detail at that bend, it's 47.5 million years, falls right in here. You might notice it's not exactly straight up right there. There's a little bit of there's an in-between segment. It's a little bit of an arc. It's really a range of 50 million years to 47 million years when you zoom in real close of when this bend actually happened, right? And you kind of see the ages here. 52 on Koko, and here 38, greater than 38, greater than 41 over here at Abbott and Kalahan. All right, so we know where all these seamounts are, and what we can do is we can then pull the rocks from these places, and we can then try to measure what the inclination of the iron crystals in that rock happens to be. And from that inclination, there's a mathematical relationship. You can say, okay, that means it was at this degree of latitude when it erupted. And so if we do that for our rocks right now, come up 20 degrees north is where we are here in Hawaii. So that's where it is. If you go back to Abbott, in fact, everything between Yuriako, Midway, Nihoa, all the way to Hawaii, everything shows up as a 20-degree north signature right in there. If you go further back on this Emperor part of the sea chain, you actually see it starts off in that same range, 23 plus or minus 2, 26 plus or minus 9, 27 plus or minus 3. Detroit's up here at 34 plus or minus 5. All right, now there can be some little variation. There's some error in here, of course, but big difference between 20 degrees north and a rock that's saying it was erupted at 34 degrees north latitude. And so that means the hotspot had to have been further north when this erupted, and then a little bit less further north, and then a little bit less further north, and then a little bit less. And then since about here, it seems like it stayed at the same latitude for some reason. Right? And that latitude is the one that we are currently at right here. This is not the only way to look at this. We actually have, it's probably too small for anyone to see here, but we have ways to look at fossils, right? You can look at sediment, like the sediments that are raining out on the deep ocean floor, and all the little critters that are microscopic that live in the ocean column evolve over time. And so there are different ones that occur at different geologic eras. You know, there are different ones that were alive 80 million years ago than are alive now, and some of the same. But the actual assemblage of them all together is also unique to time, right? So you can actually say, okay, well, if we go back, not only that, you actually can go and get the latitude of those kind of sediments, right? So what they actually find is that latitude also increases back to, they find, it's hard for you guys to see over here, but in a range of 30 to 35 degrees northward drift as well, possibly, right? As at the high end of this, and at the low end of it, somewhere around 20 degrees of drift. So the sediments are also showing, although it's really hard, I'll grant you, to both measure magnetism and sediments of an 80 million year old rock that's been submerged under the ocean for that entire time, with all kinds of stuff happening over top of it. So all with a grain of salt, but that's kind of where the thinking began, right? And what's most recent, 2017, Torsvik et al. Have done reconstructions trying to see if you could just move the hotspot down, and that's kind of now shown in this little inset down in here. This is the motion of the hotspot. Moving from, this is the best fit, I'm just showing you guys the actual result without going through all the steps, but the best location of where it started off and migrated to the south, a little wiggle, right? And through that time, the Pacific Plate was moving to the northwest. As you might think, oh, if the hotspot was moving during this time, but not moving as much during this time, then maybe this bend is just because of the hotspot. And what they're finding is that, actually, no, the hotspot does need to move to the south for sure, as much as 10 degrees of the Earth, right? That's 1,000 kilometers, that's 600 miles. The thing could have moved to the south, right? That's a long way for it to go. It's definitely not stationary at that point. But it's also not enough to account for the full bend of the seamount arc, right? So they've shown in red here what the track would look like if the hotspot, I'm sorry, if the plate had not moved. There's just the hotspot motion. And over here is a combined motion, and you kind of see these big error bars, kind of these farther ones over here, but you kind of see that we're hitting 80 where it's supposed to be 80, and 70 where it's supposed to be 70, and 60 where it's supposed to be 60, etc. It's a best approximation. So we actually had to have a change in a movement of the plate direction, and the hotspot moving from some location to the south. I can go into a lot more detail about that, but I could easily get lost there. But part of that whole process as well is that you can look at slices through the Earth based on that whole tomography, the imaging of inside of the Earth, and we can kind of see at 700 kilometers depth on this top panel over here. This is today on the left, and 60 million years ago. The flow is fairly similar, south to north. So that's kind of 700 kilometers down. For the mantle, that's shallow. That's the shallower part of the mantle. Whereas this over here, 2450 is a lower mantle. So at the lower mantle, the current actually goes north to south. Not only today, but also maybe a little bit more northwest to southeast 60 million years ago. This is something we've actually, because of all this earthquake and imaging and modeling that's kind of gone along with it, been trying to recreate what's been happening to the Earth through its entire history based on the scans we're taking today and what we know of all the materials that comprise it. it's really fascinating stuff there. And so if you look at this, south at depth, that's the motion of our hotspot. And that makes sense that that could have been the case 60 million years ago, been moving in that direction. If you found it was moving against the current, you might think, oh, hold on a second, something's wrong, or how do we explain that? But since it does fit, that kind of lends this to be the favored model. Instead of it coming from somewhere over here, farther east, and moving more west, right, which would kind of be against the current more so. So very, very brief recap of this research that's, much more in depth than this. I'm just pulling a little bit from here and a little bit from there, just so you guys can see a little bit of how this works. But here's why a plate might change its direction, right? So I've showed you guys a little bit in one view. Here's a Pacific plate in this earlier frame, 57 million years ago, the Paleocene, and its motion is in this view up, right? These blue arrows, right? Here's an emperor chain forming, and the Kula plate over here to the north, a Farallon plate is over to the east, and the Izanagi plate, the very last bits of it are over here in the northwest, right? Why? Because it's subducting underneath the edge of the continent over here, and this is the last bit of it left before it spreads under, and it's going to be completely consumed, and it's going to be all the way gone. When that kind of thing happens, like this, where this plate was the one that was moving in that direction, and suddenly it's gone, you might find that suddenly the Pacific plate now is moving that direction as well, and the Kula plate is also moving in that direction as well. Right? The Farallon plate is also in various stages of consumption over here on the right side. But that's why you might have a plate change, is because you might have an old, you're essentially rearranging. You have one less plate, the plate's all the way gone. And we talked about, I showed you some of the things about how they can detach or break off, but that's why it can change direction. And so that's what's believed to have happened. And some other kind of evidence that was going on. There's a lot going on this image here, but look here at this first northwest part. Here's Hawaii, the Hawaiian Island chain. There are other tracks of other stuff on the seafloor as well. And so one of these is called the Musicians. This is the Musicians seamounts over here. And kind of zoomed in this panel below right here. And see, these are the Musician seamounts kind of running in this similar kind of direction over here. And they have ages. It's probably hard for you guys to see, but they're written in white over here. 83 million years, 75, 86, 91, 94, 96 million years for this one up here. This is all happening early on, possibly at the same time as the early Hawaiian hotspot's active. We don't know how much beyond the 80-85 the Hawaiian hotspot actually went, because we don't see the beginning. We don't know how long it went beyond that. But so certainly by the bottom part of this one being active, the Hawaiian hotspot is also active. So you can kind of see there's multiple spots. But also what we're going to do is we're going to zoom into these little squares here and here, right? We're going to have these kind of ridges that are appearing more east-west, right? Kind of near this big Murray fracture zone, which is kind of related to the spreading of the crust, and so kind of natural weaknesses exist in the crust. But if you zoom in there, some of these show ages of 92 million years, 94 million years, so kind of similar, there was some torque, that some crack opened up, and it wasn't as simple as just one hotspot chain. But then down here in this lower section, in this area called Bach Ridge, Beethoven Ridge, they're finding ages of about 50 million years, which is about the age of the changing of the Pacific plate. 47, 48, 52, 53 are ages of all these different places. So it's almost like whole Pacific plate changed direction, torqued, opened up some gashes, and those gashes erupted for 6 million years and formed these long ridges out of the seafloor, not from hotspots. The kind of lava they find here is not the kind of lava we have here in Hawaii. It's lava that comes from this shallow mantle, as if it was just leaking up through a crack. A giant crack through the earth that lasts 6 million years to kind of plug up, right? So there's also evidence for the torque, and really you need both. You need both the plate changing direction, and you need the hotspot moving to kind of accommodate that effect. So if we go back, revisit this image here, and go back to, this is 140 million years, birth of the Hawaiian plate, or the Pacific plate. Over here, the Hawaiian hotspot is somewhere in a range of 80 plus, maybe 100. So maybe this middle frame, we're at 100 million years, might be where we actually are. And we now know that we're maybe 10 degrees north of where we are more or less now, right? That's kind of hard to see where this is on here, but it's somewhere around this zone right in here, which is just drawn on here, dotted. We don't know exactly where this was, but somewhere in the range of here, where we know there is enough heat to generate the triple junction between 3 plates spreading, right? That could be a situation, right? I'm not quite sure what this boundary over here is, right? Maybe this one isn't actually spreading, but this one is certainly spreading, and this one is certainly spreading. And so that's a zone of heat, and we have seen hotspots associated with other areas where the continents have spread apart, similar to between South America and Africa, right? And that's the whole idea of a thermal blanket, right? So when I showed you guys the picture of Pangaea, Pangaea is covering all of one part of the mantle of the Earth and none of the other. So under that area, the mantle is essentially blanketed, can build up heat over time, generate heat flow, pop up through the crust as hot spots, and then tear that supercontinent apart. So all supercontinents are doomed to break apart and travel around the globe, and then it's a globe, so they're going to re-encounter at some point, and then they come back together apart.
So how long until you get beachfront property in Ohio?
This is all geologic time. That's kind of, all like a big picture. I've zoomed way out in space and time through this whole presentation here. That's kind of where we need to go to kind of examine the origins of Hawaii. And, that's kind of something people have been asking about. And usually I don't go way out in a tangent, but that's the whole point today, is to go off on this tangent. So here we are.